we use potassium to have the template effect to close the crown. Then we make an amide formation using peptide chemistry, and we have the tetrapeptide with the aza crown. Next, we attach the 11 amino acids to the 4 amino acids, and we get the compound that's now an ion channel with a crown ether at the end. The structural consequences are that we still have the beta helix that can be shown by CD spectra in vesicles. So we still have the channel structure, and these are now the functional consequences. On ion selectivity, cesium versus potassium. For the biological channel, the natural channel, cesium is transported better than potassium, 2-to-1 selectivity, you remember. Now we have inverted the selectivity. Using the crown ether, we can go from 2-to-1 to 1-to-2. So we can invert the selectivity. So obviously, the potassium is bound best by the crown, transported through the crown, and that results in a better selectivity for potassium than for cesium. So with the ion channel engineering, we have achieved the increase of the ion selectivity by additional binding sites at the central part of the channel, and we can reverse the ion selectivity using the crown by assisted desolvation at the channel entrance. I will not go into the details on the porine work. I just show you an X-ray structure of a porine that shows you we have achieved the insertion of crown ethers into porines, and the functional consequences are a decrease of the channel activity. I guess I should not go too much into biological details, but to summarize this ion channel part, on channels with a narrow ion conductance pathway, we can tune the ion selectivity, and we are also able to work on wide pores of the porine type. Let's go back to the problems. How would you make these molecules? How would you make them enantiomerically pure? You had time to think. What ideas do you have? Let's take molecule 2 first. You can synthesize this stereocenter using a reaction a Japanese chemist got a Nobel Prize in chemistry for. To give you a hint. What would you do? To synthesize a stereocenter, you have the possibilities to make 4 bonds. This bond, this bond, this bond. Yeah? That's all you have. You can form each of these 4 bonds. Which one is the best? 2 carbon-carbon bonds, 1 carbon-oxygen, 1 carbon-hydrogen bond. What would you do? Here you are the expert. What would you do? Carbon hydrogen. Perfect. He says the carbon-hydrogen bond should be introduced. He means we should reduce a ketone enantioselectively. So retrosynthetically, he proposes that we have a ketoester as a synthetic precursor. So that would be a enantioselective reduction. Which reagent would you use? Of course, hydrogen. But which metal and which catalyst? This is a Japanese name reaction, at least for German students. I guess for you too. Which metal would you use? Palladium, platinum, iridium, ruthenium, rhodium. You use ruthenium. Ruthenium-2. And the chiral ligand is BNAP. BNAP is this. It's a chiral structure. The two naphthyl rings cannot be coplanar. So BNAP in combination with ruthenium and hydrogen is the perfect combination for this asymmetric reduction. Who invented this reaction and got the Nobel Prize for? You. What would you say? Who invented this reaction? Japanese Nobel Prize winner in chemistry. Noyori. That's the Noyori reduction. So that's first-class Japanese chemistry. And this can be used for the formation of this stereocenter. Okay, how do you make this? You cannot buy. How do you make the beta-ketoester? Make a suggestion. Make a suggestion that can be realized with chemicals available in your stockroom. So you have time till 6 o'clock after my lecture to go to the lab and to make this compound. What would you do? In order to discuss a problem, it's good to count atoms, then it's easier to talk. So you can say we form the bond between carbon 1 and 2, or so which disconnection is the best? Which bond would you form? Well, easily available and cheap chemicals are benzyl bromide and acetoacetate. These two reagents are in your department available at some place, and they can be used to form this bond. How? Well, what you need is, this is an electrophile and you need a nucleophilic position here. So you need a carb-N ion in this position, somehow a delta minus because we have a delta plus here. It would be good to have the enolate of the ketoester. If we could make this enolate, it should react with the benzyl bromide to form our product. But what happens if we treat this ketoester with a base in order to form an enolate? If we take a base to abstract a proton, which proton will be abstracted? What do you think? Which proton is the most acidic one in this ketoester? We still have our number. Which position is most acidic? You have an answer, you. 2. You are right. He says position 2 is most acidic. So if we treat the ketoester with base, we get this enolate and not this enolate. But for our concept, we need this enolate. What can we do?